Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am very happy to have Kelly Sanderson with us today. Hello, Kelly.
Hi, thanks for having me, Frank.
Well, thank you so much for going to talk about your very lovely article, which we will get to very shortly on this October 15th of 2024. And we are past equinox, so we're cooling down a little bit. At least I am in Phoenix. It was 70 degrees this morning. It was like, whoa. And
Mhm.
Kelly, where are you at? What's your geology?
I'm currently in Socorro, New Mexico at the NRAO, the National Radio Astronomy Observatory.
I did it. Very cool. Must be cooling off there in Socorro.
It's starting to feel good. A little too cold in the morning, but
Uh,
every day is good.
Very cool. Very cool. And what's your position there in Socorro, New Mexico?
I'm a graduate student actually at New Mexico State University, which is 2 hours south, but I'm here at the NRAO as a Rote-Weaver doctoral fellow.
Very cool. Um, when do you finish up?
May, this coming May.
Well, let me be among the first to say congratulations, Dr. Sanderson.
Thank you.
Awesome. Very cool. Very, very nice. And as part of that doctoral work, what do you like to do for research?
So I am interested in extended emission line nebulae, so these extended gas reservoirs around galaxies. Specifically, I'm interested in what's powering the extended emission, because sometimes it's not so obvious. And in regards to the work I've been doing lately, I'm interested in using these extended emission line nebulae with jetted AGN signatures,
Okay.
so jet-induced radio emission to try and map out the accretion history, the timescales associated with the accretion history of the AGN.
Cool. Very cool. And that is going to bring us to this very awesome APJ article. It is open access. It's the open access era, people. Go grab a copy for free. Signatures of active galactic nucleus feedback modes, a green bean galaxy with 150 kpc jet-induced radio emission. And Kelly, take us away.
Okay. So real quick before we get into the paper, I just wanted to acknowledge my co-authors here. Anna Kopinska is my advisor here at the NRAO. She is my radio expert. And then we have Maura Prescott. She is my advisor at NMSU, and she is my extended emission line gas expert. And then the rest of these co-authors are students, grad students, or undergrads. I think most of them are in grad school, actually. Yeah, that were originally part of the radio observations for the project.
Nice shout out. Very good. Okay, let's get into it.
Okay, so just a little bit of introduction about why I'm doing these timescale analyses. So we know that AGN feedback plays a major role in galaxy evolution. You know, it plays a role in regulating how much gas is available for galaxies to form stars. But to fully understand the impact of AGN feedback on these galaxies, we need to understand how powerful their episodes of feedback are and the timescales or the duration of these episodes. And so that's basically what this paper is getting at, is trying to constrain the timescales associated with different modes of AGN feedback.
Very cool. Okay.
So to do this, like I mentioned, I wanted to use two different signatures of the AGN to track what mode of feedback it's in, or it was in, and the duration associated with that mode.
Okay.
So these two different features are the extended emission line gas, which is sensitive to ionizing radiation produced by the accretion disk. So this would be during modes of relatively efficient accretion.
Okay.
And so the feedback you might get during those modes is something like maybe radiation pressure driven winds off of the accretion disk or something like that.
Right. Definitely.
And so the other signature is this jet-induced radio emission. And this is associated with jet mode accretion. And so as you can guess, the feedback you might get from this is jet-induced outflows, basically, these jets driving material out of the galaxy.
Okay, cool. I'm with you.
And so these two different signatures are actually sensitive to these accretion modes over different timescales as well. So the extended emission line nebula, sensitive to radiation from the accretion disk, over timescales around 10 to the 5 years. So it kind of depends on how extended the nebula is. Tells you the light travel size of the nebula, tells you like how far back you may be able to probe the accretion activity. And then these jet-induced radio signatures probe much longer timescales. So they're probing millions of years, up to hundreds of millions of years into the past.
Okay, yeah, so that's quite a difference, or
Yeah.
or two of magnitude.
And so in this work, we're trying to use these two signatures to map out an accretion history, basically, for a jetted AGN that hosts an extended emission line nebula.
Okay, cool.
And so I'll talk a little bit about the source if you want to scroll down to, I think it's the next page.
Next page, let's talk about.
So in order to do this type of analysis, as I've mentioned a few times, we need a jetted AGN with an extended emission line nebula. We know of a few samples of extended emission line nebulas around galaxies. For example, the green bean galaxies are the ones that our source is related to. These are galaxies at AGN at about a redshift of 0.3, and they host these extended gas reservoirs. And there's evidence to show that their AGN has actually ramped down in an ionizing output from the accretion disk. And so these are known as ionization echoes. But not many of the green beans, actually only one out of the 17 confirmed green beans hosts jet-induced radio emission. So not a lot of, not a statistically significant sample, right, to work with to do these type of analyses. But we serendipitously were made aware of a second one that hosts both the jet-induced radio emission and the extended emission line nebula. And that's the source that we'll be focusing on for this paper. This was discovered by my advisor here at the NREO, Anna Kropinska, when she was looking for, she was looking at morphologies of radio galaxies that were identified in the Radio Galaxy Zoo, which is a citizen scientist project. And so the source that we focus on here was one that was picked out of the sample because it had an unusual radio morphology. And that's not the focus of, like, understanding that unusual radio morphology is at the focus of this paper here, but we do touch on it later.
Very cool.
So yeah, the source that we are working on, we refer to it as RGB1.
Yes, because otherwise it's a very long name.
Yeah, right. RGB1, sweet and short. And yeah, and so we found that this source is a new green bean galaxy, basically, but this one has the jet-induced radio emission. And so it's a perfect opportunity for us to try and combine these two different signatures to map out the history within a single object.
Yeah, nice, very good.
So I'll talk about the data that we have collected to try and attempt this.
Okay.
So we have our radio observations from the VLA. So we obtained broadband, so 4 to 12 gigahertz, high resolution, so in the BNA configuration, low frequency radio observations. And so these also came with spectropolarimetric observations as well. Yeah, and these are going to be used to perform a spectral aging analysis on the jet-induced radio emission. So this is basically modeling the synchrotron emission to try and back out how much time has passed since those jets terminated in the external medium.
Got it.
It's essentially the age of the hotspots in the jets.
Nice. Okay, I'm with you.
Cool. And then we also got some follow-up VLBA observations, but spoiler alert, we were not able to detect the source. In those observations. We're unsure if it was resolved out or too faint to be detected, given the input assumptions.
Okay.
Let's see. And then we don't have to talk about the calibration, and everything is pretty standard. Optical observations were from the Apache Point Observatory, which is also located here in New Mexico. It's run by New Mexico State University.
Cool. go.
And so from there, we obtained long slit spectra for the source using the dual imaging spectrograph DIS and the, I forgot what Cosmos stands for. Kit Peak, Ohio State Multi-Object Spectrograph. It was in there somewhere.
Hey, very good.
Yeah, and we use those to obtain optical long slit observations of this source RGB1 with the slit aligned along the radio axis. So basically using the two hotspots or presumed hotspots to indicate the orientation of the slit.
Yeah, okay, good. Medium resolution, okay, cool. There's already okay, good, I'm with you.
Cool. Yeah, and so we obtained both medium and low resolution from those observations. And those spectra will be shown later in it's figure 1. But let me tell you about the HST observations also.
Oh, yeah.
So these were kind of exciting to get. I didn't know they existed until, a little later into the project. So it was fun to find those and fold them into the story.
A little chest of gold or something you find.
Yeah, right. And so these HST observations came from the Gems of the Galaxy Zoo HST gap filler program, which was conducted. I think it was the proposal was on the PI on the proposal was Bill Kuehl.
Okay.
And so yeah, he's collected quite a massive treasure chest of these HST observations of Galaxy Zoo objects.
Okay.
And so we got those observations. It's a broadband image centered on the oxygen 3 and H beta emission lines. And we used that HST data to basically that's giving us a view of the extended emission line gas. And so we're using that to trace out the ionization history basically of the central AGN as it's like imprinted on the gas.
Okay.
And so I'll explain more about how we derive the ionization history later in the paper.
Good. Okay. Awesome.
Yeah, and then we had archival observations that we pulled from different low frequency radio surveys, but don't really need to say too much about those.
Yeah, all good. Okay, cool.
Yeah, and so we can look at these first couple figures.
Sure, let me zoom out a little bit, get them both, and we'll zoom in as need be. Okay.
Okay, so this first figure is showing our low resolution optical spectrum. So we extracted one along the location of the host galaxy, and then the other one, we actually noticed there was a detached cloud in the raw 2D spectrum. So we took a spectrum from that one also.
Nice.
And we identified that detached cloud later in the HST image once we had gotten that. But before we were just working with, there's some kind of cloud there, not really sure what it could be. So yeah, this was the spectrum from those two components. And so you can see a lot of different, emission lines showing up. We have some, the oxygen 3 doublet that we would expect to see.
Yes.
H beta, some N2H alpha, S2 also. And then this helium line all the way to the left of the plot.
Yes.
This helium 2 line is a pretty good signature of AGN activity. And so seeing that is reassuring, to know that our AGN has AGN signatures.
Okay, those two just delimit that one. Gotcha. Okay, I'm with you on this figure.
Yeah, and then we can look at the
very nice
medium resolution spectrum as well.
Yeah, this is the low resolution ones. This was about 2000, I think, on the resolution.
Yeah, something.
It was like 3500, somewhere around there. Okay, this is the medium resolution. Okay.
So slightly higher resolution. And so it's focused in on the O3 doublet with the H beta off to the side. And then we also pulled from the bluer side of the spectrum, the O2 and neon 3 emission lines. And you see those ones aren't as strong in the detached cloud as they are in the host galaxy.
Definitely. Okay.
And for this figure, we obviously higher resolution, we wanted to look at the kinematics of the gas. And so in this top figure or top panel, looking at the host galaxy, we did see signs of, multiple kinematic components showing up there. But then the detached cloud in the lower panel has a very narrow, very small spread in its line emission. So this tells us that, it seems like the line is kinematically quiescent,
Yes. Okay.
Um,
Nice. Very nice.
yeah, and so, that's this detached cloud seemed to be coincident with one of the radio jets. And so the fact that it's showing quiescent kinematics is interesting, maybe suggesting that it's not actually undergoing a shock or an interaction with the jet. But we do see a slight blue shift in this cloud, which on the other hand would suggest an interaction with the jet. So it's pretty interesting scenario that we kind of discuss later on in the paper.
Okay. Okay. Very nice spectra.
Yes. Let's see. And then what was our next figure? I think it's the radio.
Yeah, we get into the radio properties next in the text.
Yeah. So we go over radio properties. So let's see, maybe go to figure 3. We don't really need to, these are just the tabulated emission line values, which I do use to get some line ratios for those different components and comment on the powering mechanisms.
Glad they're in there. People want to.
So if people are interested.
Numbers in that. So let's go to figure 3. And here's our radio and optical morphology. Let's see if we can blow up.
This is our object. So the bottom photo or image is the HST F625 broadband image. And then over top are the radio contours from the lowest frequency 1 gigahertz wide bin. So this is 4.5, it's 4 to 5 gigahertz basically.
Okay.
And then we have, the beam down in the lower left corner there.
Beam size.
And so in the original, the first imaging that the source was identified with, the core wasn't obvious either because it was too faint or it was blended or something, but it wasn't, a distinct, obvious component of the system. But here in our new higher resolution radio observations, it's pretty obvious that that's the core and it's coincident with this optical host.
Yes, very cool.
And so we are essentially confirming the association between those two wavelengths here.
Very cool. Good. All right.
And then let's see, there's a more zoomed in picture of the host galaxy later, so I'll just focus on the radio. So for this object, we identified 3 radio components, as you can see labeled in the figure here. We have the northwest region, so that's that northern lobe and hotspot, and then the southwest region here, at the bottom, and then the core. And so you can see actually this unusual radio morphology that I mentioned earlier. Usually you see either the 2 hotspots, far out, and then the lobe emission kind of trailing back towards the core, or you might see jets and then plumes kind of extending past where the jets are strongest.
Yep.
That's the distinction between FR1 and FR2 radio morphologies.
Yep.
This one seems to have both morphologies, based on just apparently looking at it. And so that makes it a pretty interesting source. Not only is it a green bean, which is rare in itself, it's a jetted green bean, which is also rare, and then it's got this hybrid radio morphology. So it's just a really cool rare.
Triple rare object. Very nice.
Right.
Very nice. Usually you learn a lot from these rare ones.
It's definitely been a fun one to explore.
Exactly.
Let's see. And so I comment on, we basically use our the spectropolarimetric observations that we got from the VLA. Okay. We use those to disentangle the morphology, and I'll talk a little bit more about that once we get to discussion.
Okay.
Right, and so for each of those components in that image, we extracted some SEDs, and so I think that's figure 4.
Okay, command. Okay.
Yeah, these are just describing the creation of the spectropolarimetric products.
Good. Okay. Zoom out a little bit.
Figure 4. So these are the radio SEDs that we extracted by just fitting a simple single Gaussian to each component. So the core and the southwest component are unresolved or mostly unresolved. And so we take just a single Gaussian as like basically taking all of the emission in the core and the hotspot. We think that the southwest part that we fit is dominated by the hotspot emission, not necessarily lobe. But the northern component does have some lobe emission surrounding it, as you can see, like extending off of it. And so that SED will include some lobe emission.
Cool.
And so what we do is we basically fit the shape. Do these shapes make sense for what we would expect for an active jetted galaxy? And so the first panel is showing the northeast and southwest regions. And you can see we have spectral shapes. The spectral shape is given by this alpha parameter, spectral index. And so you can see we have spectral indices of -0.85 for the north and -0.92 for the south region.
Cool. Yep.
Right, and those are pretty typical for what you would expect, maybe on the steeper side, but still pretty typical for what you would expect for an active hotspot in a jetted AGN. But the core, on the other hand, has a spectral index of -1.
Much steeper.
Much steeper, yeah, much steeper than you would usually for active cores in radio galaxies. You would expect something around like no steeper than -0.5 or so. And so yeah, this is
okay. Much smaller chi-squared too on that core.
The errors are quite a bit too.
Huh?
Right, and so yeah, and so that was a little unusual. Made us ask some questions about what could be causing the steepening of the core.
Good.
Yeah, and we'll get to that.
Good.
And then yeah, this last panel is just showing the total flux densities. So these came from those archival low frequency radio surveys that we extracted data from.
Okay.
And this is just basically getting at the total source flux, but at low frequencies. So this would correspond to the oldest plasma, basically.
Let's hear, folks.
Yeah, so it's a different frequency range down there. Once you get to higher frequencies, the plasma is fading faster. And so we'll get into it, but that's how the spectral aging happens, is like, it's a difference in how the spectrum fades depending on frequency, with how it fades with time.
Okay, good. Yeah, that makes sense. Okay, cool.
So, right. Trying to understand these better. We wanted to do some spectral analysis of the radio SEDs.
Okay.
So to do that, we used a software. It's called Broadband Radio Astronomy Tools, with a capital S at the end of tools. So the acronym is BRATS. The creator of the software is Jeremy Harwood.
Okay.
And this tool is essentially, this BRATS software is essentially used to do spectral analysis of broadband radio, resolve broadband radio maps. So you can give it a set of maps and it can either compute spectral indices maps for you. You can fit spectral synchrotron models to it, essentially. So these are the spectral aging models, and find a best fitting model to predict the age of the source. You can create model images from your best fitting model. So that's what these figures in 5 are.
Okay, very good. Let me see if I can shout out to that.
Oh, to the BRATS. Yeah, let's see.
There we go.
Yeah.
Yes. There we go. There's a shout out there. And there we go. Go check it out.
Yeah.
BRATS.
Yeah, so super powerful tool for doing this kind of analysis. And so we use this tool to perform our spectral aging modeling.
Okay.
And so you can go into the paper and read all the details of like how we determined which inputs to use and such and such.
Okay.
There's a few different models to select from the basic KP, JP, and Tribble models. They make different assumptions about the magnetic field and how the particles can move.
Okay. Okay.
But yeah, we basically, make some parameter choices
Okay.
and put those inputs into bracts and fit a JP spectral aging model. And we chose the JP model because it has a realistic description of how the motions of the particles, but it makes a relatively simple assumption that the magnetic field is constant, and so we don't have to worry about. I mean, that would probably be more realistic, but it would be a lot more computationally expensive to run those kinds of things.
Start. Yep.
Okay, and let's see. So I think figure 5 was just showing from our best fitting spectral aging model the
Okay. Figure 5.
model image of our source.
Okay, let's go down. This is post brats. Okay, bang.
Right. So this is the best fitting model, gives us this model image at 4.5 gigahertz. And then the panel to the right is showing the difference between the model image and our observed image.
Cool. Very good. Let me just absorb this for a sec. Okay. Uh-huh.
Right.
Differences in Millijansky. Okay.
Yeah. So I think the largest residual was about 0.3 millijanskys.
Very cool. Okay. I am with you.
Cool. So not too bad of a fit there.
Yeah.
And so if you go to figure 6, that will actually show the spectral age map. So
Yep.
giving the ages across the model regions.
Yeah.
And then these bottom panels are showing the error and the chi-square.
And this is the JP.
This is for the JP spectral aging model.
Okay. Wow, that's quite a spread in age. Okay.
Yeah.
Okay.
And so you can kind of see like some of those. There are some regions that aren't super well modeled, and they kind of like veer away from majority of the other pixels. What ages they're showing? So like at the top there, I think there's a slight yellow band, but you could see that it's in the chi-square map. It's associated with some poor.
Right there. We're on the yellow side. So on the really older ones, but on the chi-square, that's exactly where we're missing.
Right. Yeah, it's a little harder to get the information at the edges of these.
Yeah. Oh, fair enough. Okay. Yeah.
But so I guess the main takeaway from this one is that there are some swaths of low age regions cutting through the rest of the region. So you see like some around maybe 6 to 8 or so million years, but then this low age region, the purple one, cutting through around 2 to 3 million years.
Yeah, right in through there. That one's right in the middle, on the edges.
Right. And so these low age regions would suggest that the hotspots are present, and the uncertainties on those ages are unfortunately on the same order as the ages themselves. And so it's not quite clear from these maps if the hotspots are active or not. They are consistent with either case at this point.
Yeah. Right.
But overall, if you just take the average across these regions, so across the Southwest and the Northeast region, you'll get averages around 6 million years.
Okay.
That's suggesting to us that the total source age is at least 6 million years. But these ages are weighted more heavily by the hotspot emission than by the diffuse lobe emission, the older emission. And so these are biased towards younger ages because of that.
Okay.
And so it's likely much, much larger than 6 million years. That's just a lower limit to the total source age.
Good. Okay. I'm with you. All right.
Yeah. I'll pause there maybe and see if you have any questions.
No, I'm following you along quite well. You're doing great.
Cool.
I'm good.
Sounds good. Yeah, so that was our spectral age analysis. And then we go into the spectral polarimetry analysis.
Okay.
And so, as I mentioned before, the spectral polarimetry was used to address this idea of like, why do we see this unusual radiomorphology? Or what is the unusual morphology
Yes.
intrinsically?
Okay.
And so what the polarization data allows us to do is map out the magnetic field across the source. So in those points, those locations where we presume that the jets are terminating, so the southwest and the northeast hotspot regions, specifically the compact components, if you were looking for a termination shock, you would see something like magnetic field lines that are perpendicular to the direction where the jet is shocking. So the magnetic field lines would be going that direction.
Okay.
And then if the jet was just continuing on and not shocking into anything, you would just expect the lines to keep going that way.
Okay. Okay.
And so if you go to figure,
I think that takes us down to figures
8, sorry.
6. So we got these are the spectral maps and then polarization fractions.
Right. Yes. So these are showing the polarization fraction in the black and white image underneath.
Okay.
And then we have the radio contours laid over top. And then we have lined, the red lines indicate the magnetic field direction, projected magnetic field direction.
Okay.
And so this is the position angle of the polarized emission rotated by 90 degrees. So we measure that from our data and then rotate it by 90, and that gives you the projected magnetic field direction.
Very cool.
And so you can see, so in the northeast region, the highest intensity contours, presumably close to where the hotspot is, so where the jet would be terminating. And they do follow a pretty perpendicular direction relative to this black arrow, which is showing the direction to the core. So where the jet would be coming from.
Yeah, pretty much 90.
Yeah. So I think, and that lobe or that component, the northeast region, looks like what you would expect for a jet terminating. It was the southwest one, which we were unsure what was going on there, why it looked kind of like an FR1 morphology.
Yeah, well, that was one of the mysteries, right? Because we got both FR1 and FR2 here.
Right. And so you can see this small component here at the top of the southwest region, where the arrow is pointing towards the core. You can see that these lines are, I would say pretty perpendicular to that arrow as well. And they're all aligned, in that perpendicular direction, suggesting that the jet was also terminating at that point too.
Okay.
And so regarding the extra fluffy stuff past the termination point, it's not clear if that's actually something that's like past the galaxy, like in front, like in between us and past the hotspot, as in between us and the hotspot, or if that's something that's just projected to look that way. And it is also very, based on these magnetic fields, it seems like there's some turbulence going on.
It's dissipating here, maybe, perhaps.
Yeah. So this, unclear what the story is behind that emission and where it's located with respect to the hotspot.
Back to that. Okay, very good.
But yeah, so this is basically labeling the source as an FR2 radio galaxy on both components.
Okay. Very good. Okay. So there's our polarization fractions. Oh, here's our zoomed in version of figure 3. Okay.
Yes. So now we get more into the optical morphology of the source. So that's what this figure 8 is showing. This is the HST image shown in the blue, and then the radio contours are laid on top.
Very nice.
And then the zoom in of the zoom in is just focusing in on the host galaxy, showing the light-weighted centroid. And then someone unusual little morphology peak at some intensity peaks that surround the
Yeah.
core of the galaxy. Not quite sure. That's probably a whole other investigation into what those might be.
Okay. Interesting.
But zooming, sorry.
Stuff, whatever it is. Okay.
Yeah.
Mm-hmm.
So zooming back out to this, the nebula of this host galaxy. The dashed lines are showing the long slit from our optical spectra
Nice.
aligned with that radio axis, so you can see exactly
Mm.
what components or what emission we are picking up on.
Okay. Mm-hmm.
Yep, and then we have the beam and the size scale down in the corner. And so from this HST image, we manually identified emission sources that we thought might be associated with RGB1. So that's what the Northwest Nebula, Southwest Cloud East, and Southwest Cloud West are.
Okay. Got it. Uh-huh. NWN, SWC, East and West. Uh-huh.
And then, so we manually identified those, masked out everything else, and then masked this image down to about 3 sigma, where sigma is the off-source RMS of the image.
Okay. Okay.
And so you can see from the long slit spectrum, or the long slit dashed lines, that like what part we were getting for the host galaxy, but then also for the cloud, the detached cloud that we identified, it turns out is the Southwest Cloud East.
Ah. Okay.
So that gives an identity to our detached cloud, mysterious cloud.
Very cool. Good.
And then, yeah, we were kind of surprised to see that there's a second cloud that seems to be coincident with the radio jet location, or the termination point.
Mm-hmm.
And they also seem to be sitting on like opposite sides of the brightest point of the
Right.
termination.
Right.
Interesting.
It is. Okay.
Let's see.
Okay. Good.
Okay, and so
Get into the
to
ionization history.
yes. Oh, and so before we get to the ionization history, as I mentioned, we had that table of emission line measurements earlier in the paper. And from that, we were able to basically get some line ratios for the host galaxy and the detached cloud. The detached cloud east, Southwest Cloud East, and found that both of their line ratios are consistent with at least 75% AGN contribution to their ionization.
Okay.
So that's just confirming that they are ionized by an AGN, and there's not maybe some stars or something buried near the cloud that are ionizing it. It's AGN ionization.
Good, good. That's a good confirmation. Okay. Good.
Let's see. So then we get into the discussion. And so I mentioned that it's AGN ionization, but that doesn't quite tell us whether it's photoionization or whether this Southwest region jet is terminating into the cloud and shock ionizing it.
Okay.
But I mentioned those line profiles earlier for the Southwest cloud were much more narrow than the host galaxy. And
There's 1 and 2.
yeah, and so that wouldn't be consistent with being shock ionized. It doesn't necessarily, there's a possibility of photoionization by shocks. So maybe a shock that hasn't quite cooled, but the photons can ionize, but we also don't think that's what's going on. We talk a little bit about that in the discussion, but kind of rule that out based on just combining all the information we have so far. And so basically what I'm trying to say is we think that the most likely source of powering for those clouds is AGN photoionization.
Okay. Okay.
Sorry?
Okay, good.
Okay.
Yeah.
Cool.
Nice.
Cool. And so because we know that it's AGN photoionization, that allows us to derive an ionization profile. If it was shocking, that wouldn't allow us to know anything about the accretion disk radiation output. But given that we know it's powered by the accretion disk, we can use it to get information about that component.
Profile.
So that brings us to the ionization history or ionization profile.
All right, let's go to that one. Oops. Oop, oop.
So essentially what we are calculating is Q ion for each pixel in this image to the left, so figure 8. So for each pixel, we calculate Q ion, which is telling us what is the ionizing photon rate that's required by the emission in that pixel in order to power the recombination that produced that photon in the pixel.
I'm going to find Q ion. Here it is.
Right. And so this is our equation that we derived to estimate this. And this is based on the assumption of recombination balance. So this is saying that every ionizing photon released from the accretion disk goes into creating a single recombination line.
Yeah.
So in reality, that actually only gives a lower limit to the true expected ionizing photon rate, because you could imagine
Having a drink.
you could imagine that you might need more photons to go in to create a single photon that escapes towards our line of sight.
Okay.
And this assumption is based on optically thin emission.
Yeah, that goes for your case B.
Right.
Yep.
Let's see. And so, right, we want to do this for every pixel that's emitting recombination emission around our host galaxy.
Okay. Now
but so,
okay.
Like I had mentioned before, this HST image is centered on the oxygen 3 emission line, doublet plus H beta. We wanted to follow in line with Keel et al. 2017, because they were the ones who first did this ionization history profile. And they were working with H alpha narrowband images.
Okay.
We wanted to be able to compare with their findings. So what they did for their control sample was actually, they only had broadband oxygen 3 images for their control sample. Okay. So they took emission line ratios and essentially converted their oxygen 3 map into an H alpha map.
Okay.
For the control sample. So that's essentially what we do. We take our oxygen 3 map, use our line ratios from our optical spectra, and convert this into H alpha map.
Gotcha. Okay.
And so that is what we are using our Q ion equation on to calculate this profile here.
Okay.
Right. And so this is the pixel by pixel profile for the entire image. But we want to make sure that we're not, we want to be careful with how we interpret this profile. And so we want to smooth this profile by the minimum timescale that we would realistically be able to probe in this case.
Okay. Okay.
And so that would depend on the recombination time of the gas.
Yes.
And remember what that time is. Right. So they found, we followed Keel in picking a similar smoothing factor. And they found that the recombination time scale for a density of less than 50 electrons per cubic centimeter was about 8,000 years.
Yeah. Okay.
So scaling based on the projected distance in light years, we basically took that kernel and smoothed our profile.
Okay.
And this gave us the profile in figure 10, which is a little easier to look at.
To our smooth profile. There we go. And ionization history. Smooth. Okay. Yes.
Okay. Yep. And this is the profile. So Q ion on the y-axis, projected distance from the nucleus of the source, binned by 1,000 light year bins on the x-axis. This inset panel is showing the profile of the continuum along the radio axis. So this is extracted from the spatial profile of the source in our raw optical spectrum,
Yes.
to
Okay.
the optical spectrum.
Okay.
And so this is just showing how far out does the contribution from continuum light add to the emission? Because in principle, when you're doing your ionization recombination balance, you don't want continuum contaminating
Right.
the Q ion that you're inferring.
Right. But here it's all basically on the inside.
Right.
Right.
It goes out to maybe, I don't know,
40,000,
something.
maybe here.
Yeah. Right. And so, yeah, we don't think it's really contaminating much of these other components. And so, yeah, I'll mention at the top, we've marked the location of the different components identified in the optical image. So the oxygen 3 center, so basically the center of our nebula is marked with that first line. Just under 4.5 arc seconds, we have the Northwest Nebula.
Yes. Okay.
And I'll admit we don't have much spectroscopic information on the nebula, but we can't for sure say that it's powered by AGN photoionization. But I will note that whether or not we include it in this analysis doesn't change our main results, so we leave it. And then yes, this dashed red one is the Southwest Cloud East, which we do have a spectrum for, and then the final one is the Southwest Cloud West. And you can kind of see their locations popping up by these like bumps along the profile.
Yeah, it's not smooth.
No, not smooth. But we do see this, very obvious decline as you move from the outer clouds towards the nucleus.
Yes, that's good.
And this is essentially the shape of the profile that Keel et al. Saw when they compared fading AGN with these extended nebula to a control sample of active AGN. They saw a very prominent decline towards the nucleus, whereas the active sample was kind of leveling off to a consistent value towards the nucleus.
Nice, very good.
And so this is essentially, I guess I would say one of our money plots.
Hey, money plots. We like money plots.
Yeah, so this is suggesting that there's been a decline in the Q ion output of the nucleus over the past roughly 150,000 years. And a pretty substantial decline. It's about 2 orders of magnitude.
Ooh, at least, yeah, 54, 56. Yeah, 2 orders of magnitude, certainly. Plus. Very good. Okay. We'll take that one as the raster image. Very cool. Very good. And then we go into discussion of the timelines.
Right. So yeah, and then we try and combine this information that we've garnered from the different timescale analyses. So starting with the ionization history. Right. So one of the most basic estimates you can make with these extended emission line nebulae is what's the minimum duration that the AGN must have been on in order to light it up all the way out to whatever distance, X distance.
Okay.
Basically the light travel time of the nebula. And so
yes.
I believe it was, it might be a little bit more up in the paper, but sure. We essentially measure the size of the nebula and take that as our light travel distance and estimate that it would have taken the AGN at least 0.1 million years. So that's about 100,000 years to light up this nebula all the way out to these southwest clouds.
Okay. Okay. Then we're in the Q's, and I saw that 0.15 in here somewhere. Okay. Yes. Very good. Timescale.
That gives us a minimum duration, at least 100,000 years. And then our ionization profile tells us that there was a decline in that Q ion by about 2 orders of magnitude over the past 150,000 years.
Okay.
Right. And so that's just basically placing those constraints on the radiative output of the accretion disk, the timescales associated with that activity.
Nice. Okay. Very cool. Well, I'll find it in here somewhere. Yep.
So that is kind of telling us that this RGB1 source is a light echo, an ionization echo, because
Yeah.
the gas is still showing signatures of AGN, but the core is showing this decline towards it. And we know that it's visibly similar to the green bean galaxies, but the green bean galaxies all were selected as ionization echoes using a mid-infrared oxygen-3 selection technique.
Yes.
And when we try and use that selection technique on this source, it doesn't pass the technique. So it wouldn't be selected as an ionization echo, even though it is, which was interesting. And so we
Okay.
discussed a little bit about what would cause
Yeah.
discrepancy.
'Cause if there's one, there's more.
And so one thing we possibly discuss is maybe there's not enough extragalactic gas for the oxygen-3 to be as bright as the green bean's
Okay.
oxygen-3 emission is.
Okay.
Or alternatively, maybe there's just different host galaxy properties between the two samples. And so we actually use some WISE photometry to look into that.
I understand. Okay.
So using the WISE photometry, we look at the SED of the core of the host galaxy, and we notice that it's not quite a power law like what you would expect for AGN powered mid-infrared emission.
Okay.
Whereas the green bean galaxies all seem to have power law mid-infrared emission.
Okay.
But what's interesting, and I think I don't know if I didn't actually quote the green bean luminosity here, but I found that it's actually quite similar to RGB1's 22 micron luminosity. So they have similar 22 micron luminosities, but different. The green beans show AGN powering in theirs, and the RGB1 does not. So that maybe is suggesting, is there just more star formation going on in RGB1 that could be making up for that difference in luminosity? So that's just one idea we played around with.
Good. Got it.
And then for the spectral ages, we also use those to place constraints on the activity. And so the steepness and faintness of the core might suggest to us that maybe the radioactivity is fading or changing in the core or something, a change in accretion rate, something like that. But the spectral ages of the extended components are inconclusive, as we saw with the high uncertainties on the order.
They were just as big as the value themselves on those. Yes.
So it doesn't tell us whether it's currently active or not, but does give us information about the total age, which we know is at least 6 million years, if not more. And so combining those two pieces of information, the constraints we have on the radiative ionizing photon output and the radio mode accretion, we think we have this picture emerging of, was this galaxy a high excitation radio galaxy? So these are called HERGs. And so we think it might have been a HERG.
Okay.
But the question is, are the radio mode and the radiative output mode, are they declining at the same time? Or did the radio mode start declining before the rise and fall in the optical mode? That's what's unclear about the combination of the information. Or alternatively, if the radio output is not declining or decaying, is this just a HERG that's transitioning into a LERG, a low excitation radio galaxy? That would be the other emerging picture.
So indeterminate at this point.
Yeah. So yeah.
We'll come back to that.
We'll come back to that. Right. So that was the main goal of this paper, was to try and map out this accretion history. But we also had some bonus results. We identified that detached cloud coincident with the southwest jet termination point. That's suggestive of a jet cloud interaction, we would think. And so we kind of go through like how realistic is that based on the other information we have? And so we saw like the narrow emission line wouldn't suggest a strong shock is ongoing, but there are ways around that where you could get a narrow emission line with a strong shock also.
Okay.
But it would have to be a new shock, a fresh shock that's actively that like it would have to be an ongoing shock.
Yes.
And
Okay.
based on our uncertainties on the spectral aging, it's we can't rule out an ongoing shock. But
yeah, sometimes things have more mysteries as you discover stuff about them. Very good.
That's fun. Let's see. Yes, so this was where our VLBA observations came in. And so, right, you would think for a strong currently active shock, you would be able to detect it at VLBI sensitivities and angular resolutions.
Yeah.
And so that was our whole purpose for proposing for this time, was to try and get a better idea of what was going on at that southwest termination point.
Yeah.
But we actually weren't able to detect anything. So using that, we kind of make some estimates about, well, how bright or large might it have been for us to not have detected it.
Okay. Yeah. Yeah.
And so we think maybe, I guess one possibility is that because our radio galaxy isn't as bright as the other, bright or as powerful as other radio galaxies where you can see active hotspots, maybe it's active, but we just can't see it because it's not like the other ones that have been seen.
Okay.
Or alternatively, if we interpret our spectral ages as saying that this source has recently become a remnant and that the hotspots are maybe 2 to 3 mega years old, it's possible that the shock could have dissipated. Like if the gas was shocked into the southwest cloud, perhaps that shock has already dissipated and the gases become quiescent again.
Okay. Okay. All right.
So these are different possibilities that we throw around.
Very cool. Okay.
And then we comment on the radiomorphology, but I already talked about that previously, so we can skip that section and jump to the conclusions.
Okay. Very cool.
So I guess what I'm really proud about with this paper is that we brought together these different multi-wavelength analysis techniques to basically paint a better picture of what could be going on inside this galaxy than either technique separately would give. And it's really just highlighting the power of combining these different timescale analyses to map out what's going on in a single AGN.
Yes. Very cool. Beautiful. Beautiful work combining all that. So yeah, I'm glad you're happy about that or proud about that. That's very cool. Very good. Kelly, I want to thank you so much for walking us through your very awesome APJ article. Thank you.
Oh, thank you for having me. It's fun to talk about.
And let's see, you mentioned it a couple of times, or at least there was stuff suggesting themselves as we went through. Let me just push on that a little bit and ask, where do you think we go from here given the published article? We have a number of mysteries that this work uncovered. Ways to go ahead and resolve those mysteries. Is there additional data? Is there additional models to consider? Is there new data coming, maybe at even additional wavelengths, and so on. So just sort of next steps, what you think those are on this object.
Yeah, good question. So yeah, I mean, I think one of the biggest open-ended things from the paper was what is the spectral age of those radio hotspots? Our uncertainties were too high for us to be able to distinguish. And so I think more resolved spectral age modeling at lower frequencies, which would be sensitive to the oldest plasma, the original termination of the jet, would hopefully help us be able to to get better constraints on the spectral ages in those regions. And so with, the new low frequency arrays that are popping up,
Yep.
that should hopefully, be feasible.
Do you have any telescope time proposals in?
Not currently. Working on some other stuff right now, but that's definitely an idea for future project.
Pick it up, people. Pick it up.
Yeah, yeah, for real. Right, and then other next steps. It's not quite clear. Like, we have argued that there's not an ongoing shock, based on our long slit data, which only captured one of the clouds. So getting IFU data, more spatially resolved spectra across both cloud complexes,
Yeah.
I think would help us to do some more, some modeling basically of the temperatures and densities in that gas. Is it consistent with a shock model, or is it consistent with what we think quiescent gas would look like?
Cool. Very nice.
And then just expanding the sample. Obviously, I said this is a project.
Yeah,
Let's find some more of them. Yeah.
Yeah, of course. I should ask that. We got one. How about 10? Let's get 10.
Yeah, right. 10 would be nice.
That'd be cool. Very good.
That's the next step.
Yeah, well, it'll be really exciting to see this this topic develop over the next couple of years, both on this individual object and its peculiarities, and hopefully it has some other friends around, and we can see how those go. So it'll be very cool to see. Very nice. Yeah. All righty. And that will, thank you, Kelly, so much for walking us through all that.
Thank you.
And that will do, everyone. And I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.